the most important concept in calculus, the derivative. A sequence of actions, if we replace an action by a function, that's also a function. We've already seen examples of this. I feed x through the square function, and I feed that through the sine function, so I get sine of x squared. That's a function, but it's also a sequence of functions. We don't need to just do elementary functions. As long as we're looking at something that's a one input, one output, you can be anything I want, like plotting a point. That's a function. And I'll plot another point. Now I've plotted 2 points. If I have 2 points, I can compute a slope. This sequence of functions is also a function. So let's do something. So I'll plot a point. Then I'll plot another point. So I have my first point already. And I plot another point. I'm going to think of it as being a horizontal offset away from the first point I plotted. Plug that into my function. And now I can compute my slope. 2 points. So I need my run, h units, and I need my rise, which will be the difference of those 2 coordinates. F of 3 plus h minus f of 3. So my slope, I go up, I go over. That fraction is my slope. One number output, but my input was 2 things. So right now it's an action. It's the difference quotient of f at 3. To get this launched, I need a function rule and I need an input point. So 2 things. And coming out, I just have one thing, one number, the slope number. Notice I'm writing it all down, and the only thing I need is the function rule and the number 3. I'll do our trick from last time. If I think of it as an ordered pair, a function input ordered pair, now it's one thing in, one thing out, and we'll call the slope what it really is. It's a secant slope. Now that's a function, one in, one out. And the function's name is the difference quotient. The output then is the difference quotient of f at 3. For our derivative, start with our difference quotient. And now we're going to drive h to 0. This will give me a number, and this is the label we use for that number. This is a new function. It's called the limit. The limit as h goes to 0 in particular. This sequence of functions is the derivative. One input, one output. So the output is called the derivative of the input, f at 3. Let's look at the limit a little more carefully. We'll just do it with an example. So I've got some function, and I just draw a graph. Coming from the left it's 3, coming from the right it's a 4, and this is at some point. Label our axes, and label our function. So y of x, the limit as x goes to a from the negative is 3. The limit as x goes to a from the positive side is 4. Another way of saying the notation, limit as x goes to a from the negative of y of x is 3. Limit as x goes to a from the positive side of y equals 4. Same thing, different notation. This limit does not exist because they don't match. So let me change the function to make the limits match. Now the limit exists. But it's not the same as the function value. This is the definition of continuity. If the limit of x goes to a is y of a, it's continuous. Otherwise it's not. One last thing to look at is differentials. So let's review how the derivative happens. Given a function rule and an input value, I assemble the difference quotient, which is the secant slope of the function at that point. And then I take the limit as h drives to 0. I output a number. That number is the slope of the function at that point. So let's put all this together in a picture. There's our point, and now we have a little slope that we've constructed. And this is called the slope of the function at that point. So the derivative is a slope function. A slope, of course, is a rise-run ratio. So the run is a push along the p-axis, the rise a push along the f-axis, and the labels are df and dp, and those are called differentials. The ratio of the differentials is your slope. We'll use this schematic quite often. We'll call this the calculus schematic. We're plotting position and slope. So you can think of the derivative as saying that the function looks like a little line piece instead of a point.